Today we're going to talk about RV Android, a brand new runtime verification technology by Runtime Verification Inc. To give a brief overview of Runtime Verification Inc., we are a research-based startup operating out of Research Park at the University of Illinois at Urbana-Champaign. Our staff includes leading experts in the academic world of runtime verification. We also collaborate extensively with our industry partners, including the Toyota Info Technology Center, with funding from Toyota and Denso America, under whose contract we initially created the RV Android technology for the automotive domain. Our products include RV Monitor, a commercial extension of the academic Java MLP tool. RV Monitor allows the user to use one of several mathematical formalisms, including context-free grammars, extended regular expressions, finite state machines, linear temporal logic, past-time linear temporal logic, and string rewriting systems, to define mathematically rigorous safety properties of running applications and enforce them at runtime. As you can see, RV Monitor monitors around 200 Java API properties on a DiCapo benchmark, with almost 3 times less overhead than Java MLP, bringing it to within the realm of practicality for use on mobile devices, where overhead directly translates into performance and battery life constraints. A developer prototype of RV Android for Android developers is available on our website at runtimeverification.com/android. Bundled with the RV Android download, we provide several examples illustrating the correct use and syntax of the RV Monitor and RV Android tools, with Java instrumentation across several formalisms, including extended regular expressions and linear temporal logic. If you are new to RV Monitor, the RV Monitor/examples subdirectory is a great place to begin to familiarize yourself with the syntax of writing RV Monitor and MLP files. In this example, we consider a safety property of the Java API, namely that for a given iterator, before any call to the next method is made, at least one call to the hasNext method must be made, ensuring that the end of the iterator has not been reached and an exception will not be thrown by the next method. We first define the property, which is parameterized or conditioned on the iterator object it describes. We model the correct execution of this program as an extended regular expression, consisting of a hasNext event, followed by some number of hasNext events, followed by a next event some number of times. If at any point in the execution trace of our program, for a particular iterator, this extended regular expression can no longer match the sequence of events generated in any case, this failure state will be reached, and the associated code will be run. We can now test code, in which a vector of integers is created, 4 numbers are added to the vector, the iterator is extracted to the vector, and then the iterator is iterated through, adding all the integers in the vector to the variable sum. We can see here that the execution of this program is not safe with regards to the property we defined, as hasNext is called only once, while next is called 4 times. We expect then to see 3 warnings in the console about the fact that hasNext has not been called next for a given iterator. We first compile our monitoring library using the RV Monitor command and passing it the RVM properties file that we just defined. Notice that in the original code, calls to the hasNext runtime monitor library are inserted manually. For RV Android, this is not the case, as we generally use automatic instrumentation with AspectJ, or the MLP capabilities of the RV Monitor tool. In this fashion, we're able to completely separate the runtime verification portion of the code from the actual codebase itself. To test our monitoring library, we now compile it together with the original program using standard Java compilation commands. Running the program, we now see the expected output, namely warnings 3 times that hasNext has not been called before calling next for a given iterator, as well as the original output of the program. While we encourage you to further explore the examples provided with the RV Monitor directory, we will now consider the RV Android examples provided. The first example we provide is a simple media player application. If you are at all familiar with Android development, you will recognize the contents of this directory as the default directory contents created by the Android SDK when starting a blank project. We now consider a single activity, the monitored app, whose role is to properly start a media player and play some music. Notice the call to mediaplayer.start here. Notice that this code is unsafe with regards to the Android API, which states that a call to mediaplayer.start should only run after the associated media player is prepared. One way to ensure this is to run mediaPlayer.start inside the onPrepared listener, which runs after the media player is prepared. Comprise execution. Consider the RV monitor file that comprises a formal model of the correct execution of our program with regards to the safety property of the Android API we just described. Rather than parameterizing on the media player we are looking to fix, one possible verification option, we instead in this case store it as an instance variable of the generated monitoring library, allowing us access to fix any incorrect calls to mp.start. Notice that the property here is described as a linear temporal logic property, stating that we must see setOnPreparedListener at least once before we see the start call. We can just as easily describe this property as a context-free grammar formula, with one event for the beginning of the setOnPreparedListener call and another for the end, ensuring that our call to start occurs in between the beginning and the end of the setOnPreparedListener call, or between the two events indicating the beginning and the end of the setOnPreparedListener call. We choose to avoid this for simplicity. We now enforce the correctness of our program's execution with regards to this property. When a violation of our linear temporal logic formula is detected, we first show an alert to the user using the alert dialog builder provided with Android and the __activity RV Android runtime environment keyword. This keyword allows the author of the RV monitor files access to method calls and data structures inside the Android application being instrumented, providing the basis for our Android recovery model. Notice that we also correct the execution of our program by ensuring that the call to mediaPlayer.start is made inside an onPrepared listener. To accomplish this, we use the RV monitor runtime environment __skip keyword, which together with instrumentation around the original mp.start call allows us to skip the execution of the original code, executing our correct code instead and enforcing the formal property we defined. Another new directory we create in the default Android projects is the aspects directory. This directory allows us to use aspect_j for weaving our monitoring code into our application at compile time. Notice here a standard aspect_j file. In this aspect_j file, we provide 3 instrumentation points for our application. The first is before the execution of the activity.onCreate method on a given activity, and calls the onCreateActivity method of our setOnPreparedListener runtime monitor, generated by the RV monitor command we will show next. This is required to keep track of the current activity for use with the __activity keyword, and is required for any RVM file that uses the __activity keyword. The next 2 instrumentation points we provide include one after any call to mediaPlayer.setOnPreparedListener, simply firing the setOnPreparedListener event of our generated library. Our final instrumentation point corresponds to the start event of our generated library. It occurs around any call to mediaPlayer.start, with the target being m, which is passed in as a parameter to our start event. The following 3 lines are extremely important as they enable the use of the __skip keyword we showed earlier. This allows us to enforce our property by ignoring the execution of the original code provided. Besides the RV monitor properties and aspect code for the weaving of the RV monitor properties, the only additional files we need to provide over the original Android project are 2 libraries in the libs directory included with the RV monitor download, the aspect_j runtime and the RV monitor runtime, as well as the custom rules.xml file that we provide again with the RV Android download. This custom rules.xml file defines an ant task to be run after the compilation of the Java bytecode in the default Android build process. There are now only 3 steps remaining in the process of building our application with RV Monitor. The first is to synthesize our monitoring library from the RV Monitor property file, as before. We do this again through the RV Monitor command. Then we must manually copy the generated library into our source tree at the location specified by the package of the RV Monitor file. Both of these steps can be automated by the developer into the ant script. The last step is to simply run the ant script as usual. As expected, the monitoring application is now installed on our phone. When we open this application, we again see what we expect, a pop-up stating that the media player has been called without setting the prepared listener, and that the listener is being set. The next example we provide is OSM Tracker Android, a real open source software clone of a popular Windows mobile application called OSM Tracker. This application is non-trivial in size, allowing the user to take pictures, track themselves via GPS, save their tracks to disk, share their tracks, and much more. This application was chosen for its similarity to the automobile dashboard navigation apps, which are often Android-based. The build process for this application is identical to that of the simple media player we showed earlier, so we'll focus instead on the relevant properties we provide in the MOP properties folder. The first property is a standard property of the Java API, called a closable multiple close. This property specifies that for a closable interface C, close can be called only once on that interface. We therefore both parameterize this property on a particular instance of a closable interface, C, and describe the property with an extended regular expression, describing in this case the incorrect rather than correct execution of our program as a close event followed by at least one other close event. Notice that both every time a close event is fired, and if this extended regular expression matches, we log something to Logcat, the standard Android logging facilities in the RV-Monitor category. This demonstrates the remarkable ability of RV-Monitor to extend both the verbosity and specificity of logging on Android, and indeed on any platform in which it runs. In the case of a double close, we also skip the second close event. The last, and perhaps most interesting property we consider, is a property of the Android API. Unlike the previous property, which was adapted from a standard repository of around 200 Java API properties, this one is specific to the safe use of the Android API. This property deals with the getSystemService method of the Android API, responsible for returning a system-level service after the application has been authorized by the Android permission system. These system-level services can often be used to leak potentially sensitive information about the user or the device from one of many sources. We therefore choose a select number of services, including the location, SMS, telephony, notification, and storage services, and create RV-Monitor events for their access. In the standard Android deployment, there is no way to log which application is getting which system service at which time. This important feature has been the subject of previous work on Android security. RV-Monitor allows you to do this easily by simply inserting logging code into the RV-Monitor event on which you are interested. In this way, you can easily log the access of system-level services to Android's Logcat in user space. The next thing we do is provide an extended regular expression which details one possible method of data exfiltration that can occur on Android. This is if the system-level telephony or text or location services are accessed at least once before the storage service. While this sequence of events is likely a normal mode of operation for many Android applications, it is easy to imagine a situation in which location, telephony, or text service must be strictly protected, such as the use in the automobile of a diplomat. In this case, the exfiltration of data is a grave concern, and strict properties like this can be defined by the user in order to protect themselves from rogue applications. In the event that this property is violated, as in several previous properties, we use the __ activity keyword to show a dialog informing the user of the violation. You can easily build the OSM Tracker application with these properties as previously described by simply using RV-Monitor to synthesize the monitoring libraries. You can see that when installing the OSM Tracker Android application, it requests permission to record audio, get precise location, modify and delete the contents of USB storage, and get full network access, as well as the access to protected storage. While these properties may seem innocuous by themselves, they could possibly lead to the leaking of location information through the USB storage, one of the properties that we do test for. Opening this application and recording a new track, we require it to begin tracking and access the GPS service, which then opens a pop-up saying that a possible data exfiltration event has occurred, either by telephony, SMS, or location services. While this violation of our property was not in the code of the original OSM Tracker Android, which did not actually violate this property, we modified the code to illustrate an example of the violation of this property and the notification of the user that the property is being violated. To find out more about RV Android or our company, simply visit runtimeverification.com and runtimeverification.com/Android, where a download of the developer prototype of RV Android is available. We will also be developing several user space, user-friendly apps around the RV Monitor technology, so check back frequently at this location for more updates. Thanks for